How can we ensure that when two people are working on the same resource, an update of the resource by the first person no longer overrides the changes the second person made in the meantime? That's what we're going to deal with in this module, supporting concurrency. I'm Kevin and I'll guide you through it. So, this module is all about concurrency. We'll start by looking into an example of how we can support concurrency in a RESTful world. Afterwards, we will dive into a demo in which we'll again use e-tags to correctly support this. Let's dive in. Let's start with an example. Say two users, Kevin and Sven, are working on a specific resource at the same time. For example, they are working on the same author. They are thus client instance 1 and client instance 2, as they're both running the application on their own machines. Kevin gets the author, and a bit after that, Sven gets the same author. Sven edits the author and issues a put request. The author has been updated. Now Kevin, who is finally done editing, issues a put request as well. At this moment, Sven's changes are lost, and that is a problem. I'm guessing this is a familiar concept for most of you. Issues like these, concurrent updates, are handled with a concurrency strategy: pessimistic or optimistic concurrency control. Pessimistic concurrency control implies that the author would be locked for Kevin. As long as it remains locked, it cannot be modified by anyone else but Kevin. So the name, pessimistic, implies that there will be some sort of fight over the resource. This is not possible in REST, as one of the constraints is statelessness. Then there's optimistic concurrency control. This implies that Kevin gets a token that allows him to update the author. As long as the token remains valid, Kevin will be able to perform the update. Optimistic implies that there won't be an issue, but if there is, the token will tell you that. Optimistic concurrency is possible. And that token, well, we learned about that already. That's actually a validator. A strong validator is required for handling issues like these, so we can use e-tags for that. Let's go back to our example. Kevin gets an author, and the author is returned with an e-tag value. Sven gets that same author, and that's returned with the same e-tag. Sven updates the author, passing in the e-tag in the if-match header. The API checks this header and compares it with the e-tag it saved for that response. If they match, which they currently do, the update can be applied. At this moment, a new e-tag is generated for the response. The response then includes that new e-tag as well. But then Kevin sends the update with an if-match header containing the e-tag Kevin currently has. It reaches the API, and there the API sees that this does not match with the most current e-tag for that resource. So the API returns a 412 preconditioned failed status code. Kevin's update isn't applied because he was working on an older version of the author. And that's how this works. The same applies for patch, of course. This also drives the case for separating the cache store from the component that just generates the cache control and e-tag headers. Those e-tag headers serve different purposes. We don't need a cache to handle concurrent updates. So, even without putting a cache server in front of the API, or without using a content delivery network, we can support concurrency simply by having a component that generates e-tags for us, by sending them from the client, as we just learned. Let's have a look at how this works with a demo. In this demo, we will have a look at how e-tags can help with concurrency. The first thing to do would be to create e-tags for our resources, but we don't have to do that. The marvin.cache.headers middleware to generate e-tags is already in place. The response caching middleware is still disabled. This is as it should be, as we learned. I've opened up Postman. Let's assume that we are user Kevin. And let's get a course. If you look at the response headers, we see that we get back an E tag. Now, I cannot open two instances of Postman next to each other, so we're just gonna simulate that we're another user now. So let's keep this in mind, and now let's assume that we are user Sven, and get this course again. We get back the exact same response with the exact same E tag. That makes sense. It is, after all, the same response. So both Kevin and Sven are now working on the same response. It is still Sven's turn, and Sven is updating the response. After he is done, he sends a put request. Let's send that request. And we get back a 204 no content, meaning that the request nicely updated the resource. So that's good. What we also see is that a different E tag has been generated for the response. That makes sense. Marvin.cache.headers takes the response body into account when generating E tags. Let's now assume that Kevin is done with his update and he also wants to send the put request. So let's change the title and description a bit. And let's send it again. This one nicely updated the resource as well. And that is an issue, as Kevin has now overwritten Sven's changes. So this is not what we want to do. We're going to fix this. Let's start again from scratch. So here we go. The first step, Kevin gets the course. So we send the request. Here's our response, as expected, with an E tag. Let's note down this E tag somewhere. We'll need it soon. And then we are Sven. And we send the same request and get the same response with the same E tag. Alright, it is still Sven's turn. And Sven wants to update this course. So he wants to send a put request. What should happen now is that the consuming application, which is the application Sven is using, or possibly an in-between cache if we have that installed, well, that should take this E tag value and put it in the if match header for our put request. In our case, Postman is the client application that is sending the request, so we can manually add it. In reality, it's either code in the cache or in your client application that does this. So we pass through an if match header with the E tag as value. Let's send it. And we get back a 204 no content. The update went through. That makes sense. We sent a put request stating that the E tag of the resource we are updating should match what we pasted in here. And that is indeed the case. If we get this course again now, we also see that a new E tag has been generated. But Kevin is still working on his copy. He hasn't got the most recent copy with the new E tag. So Kevin sends a put request with that old E tag as an if match header. Again, this is something the client application or an in-between component must do. It is not something Kevin or Sven should manually do. What we get back now is a 412 precondition failed. The update isn't allowed. This tells Kevin that he should first get a fresh copy to work on. Like this, we've implemented optimistic concurrency checking. That's it for this demo. Let's have a look at the summary. The E tags we used for validation can also be used as a token or validator for an optimistic concurrency strategy. This allows concurrent users to work on the same resource without running the risk of accidentally overwriting a newer version of a resource. For that, we, or rather the consuming application, sends the E tag in an if match header. If the E tag doesn't match with the E tag the server generates for the resource, the update will fail with a 412 precondition failed status code. With that, this course is done. I hope you enjoyed watching it as much as I enjoyed making and recording it. If you happen to have any questions, feel free to send me a message on Twitter or use the discussions tab on the course page. Also, please consider rating this course. It's very helpful for us authors. Before I go, I only have one more thing to say. You're ready to be awesome.